So in this experiment we're testing two materials, steel and aluminium. On each material there'll be two tests. The first test would be load each sample within the elastic range, and that will be using an extensometer to measure the extension. We'll just be applying a tensile load up to an extension of 0.03 millimeters relative to the extensometer. When that is reached, the machine will stop and we'll remove the sample. The second test that we do will be repeating the materials, but this time loading each sample to failure. But we will not be using the extensometer to measure the extension, we'll be using the machine crosshead. And the machine will continue to load until each sample fails, the crosshead will stop, and then we can remove the sample. So prior to carrying out the test, we need to take some measurements of each sample. So each sample, using the digital vernier, will measure the diameter in 3 places. So this position at the moment, we've got a diameter of 5.05. You'll be given 3 diameters, you need to take the average diameter. But also, we need to take one length measurement. So this measurement is 110 millimeters, and you're going to be given the values for the aluminium. So that's with the digital vernier. Also, you need to use this device. This is a percentage reduction in area gauge, and it needs to be set to 0 before we start the test. So imagining a center line for your sample, you will set that up to the 0 line, and then it's locked and then left. We will use this again once the sample has failed, and we'll show you how we read that afterwards. Coming back to the extensometer, with the pin located, it will set the distance between these two knife edges of 25 millimeters. This is the gauge length of the extensometer, which you will need in order to calculate the strain for when we're testing within the elastic region. It will be the extension divided by this gauge length. For the test to failure, strain will be the extension divided by the original length of your sample. So test 1 will be loading the sample within the elastic region. In order to set the sample up, we're going to use these split collets. So the sample sits in the shoulder, the 2 collets come together, the ring is placed over the collets, and then the unit is placed at the base. The pin goes through the split collets and through the clamping fixture. We do a similar thing for the top. 2 collets, place over sample, the ring, bring that up, the grip, place the pin in. Now, the system is all loose at the moment, the sample is loose. So we need to apply a preload of approximately 100 newtons onto the sample, approximately. When we have that, we're then going to set up the extensometer. Place that somewhere in the middle. Now at the moment the pin is in, that's just setting that gauge length of 25 millimeters. When we're ready to do the test, we're going to pull the pin out. The still sample is now reset without the extensometer, because we're loading the sample all the way to failure. We're anticipating failure to occur along this portion here. So we're just about to start the loading, and just to keep an eye on our sample. So load is being applied. So we're looking for that central section of where the diameter reduces, and we call that necking. So we are now gone to 4 millimeters extension based on the total length of the sample. 8 millimeters of extension, approaching 9 kilonewtons. When you observe the graph, you'll see the graph reach a maximum and then the graph drop off. When that graph starts to drop off, that's where it indicates the sample is starting to neck. We're reaching a maximum load, we're at 12 millimeters. The graph now is starting to drop, so somewhere along our length we should be seeing the sample neck. We're at 16 millimeters now. The load is dropping off. It's starting to neck. Failure occurs, the crosshead stops. It's now safe to remove the sample. But once the sample is tested, we need to now take some more measurements. So for one portion of the sample, we're going to measure the percentage reduction in area. So we can take the left or the right portion. We're going to measure where the diameter is the smallest at the necking area. And what we do is we will slide it down the percentage of reduction area gauge, and then we'll read off the value. So in this case, we're looking at approximately 55% reduction in area. But you will be given the data for the steel and the aluminium. So this is percentage reduction in area for the steel sample. The second thing that we're required to do is to bring the two portions together and then measure with the calipers, measure the final length. And again, you will be given the values of that for the steel and the aluminium. So in your results and calculations, obviously there is a number of points that you need to consider. There's a number of graphs that you need to draw to produce, but be careful of your units. The units that you have from the test will be in millimeters and newtons. But here you need to produce a graph of the load in kilonewtons. And our stress, we're asking you to produce a stress of units of meganewtons per meter squared or megapascals. So be careful of your units. Obviously strain has no units. You're given a list also of things that you are required to calculate, from Young's modulus, tensile strength, 0.2% proof stress, the percentage elongation to fracture. Now the percentage reduction area of fracture you don't need to calculate because we're going to use the data from the percentage reduction area gauge. Use the graph here to assist you to work out the percentage, the 0.2% proof stress. Use this graph here for that to guide you.